Alright, let's begin. So, I gave y'all a handout. Y'all can use to copy the notes from the PowerPoint from. So, we make qualitative observations of reaction. Qualitative refers to the quality of something. Observations that describe quality, such as color or physical change. And we also make quantitative observation, like quantity, how much, that involve measurements with both numbers and units. So, there should be no naked numbers. A measurement always has two parts. A value, this is the number, and a unit of measurement. This tells you what you have. For example, 500 or 200 meters, 15 milliliters, 13.98 grams. I am very particular about units, or I should say, I find units very important. You will always get 1 point off if you do not include a unit. So if I give you a homework assignment with 20 questions and you don't put units on all 20, that's 20 points off. So in chemistry, we'll use the SI units of measurement. So the international system of units. These are the base units that we will work with. We have mass, which is done in kilogram, it's abbreviated as kg. Length, which will be the meter. Time will be seconds. Temperature, Kelvin, and amount of substance, mole. We'll probably be dealing more with grams instead of kilograms, centimeters instead of meters. A milliliter is a cubic centimeter. I believe a cubic centimeter and milliliter are the same thing. So from these base units, we can combine them using mathematical operations to attain derived units. Some examples of derived units would be density, which is grams per milliliter, area, which is meters squared, and volume, which is cubic meters. Kilo means 1,000th of that unit. So you have a kilometer, often just pronounced kilometer. I usually pronounce it kilometer, but it's kilometer. Kilo means 1,000, so 1 kilometer is 1,000 meters. Centi means 100th of that unit. 1 meter is equal to 100 centimeters, or equivalently 1 centimeter is 1/100th of a meter. $1 is 100 cents, or 1 cent is 100th of a dollar. Milli means 1,000th of that unit. 1 meter is equal to 1,000 milliliters, or 1 millimeter is equal to 1,000th of a meter. So I got these from Miss Anglin. Miss Anglin likes mnemonics. To convert from one metric unit to another, remember this mnemonic. King Henry died unexpectedly drinking chocolate milk. Either way, same difference. King Henry doesn't usually drink chocolate milk. However you remember it, you can draw a line on a piece of paper with 7 tick marks. Above the tick marks, write the abbreviations from the King Henry mnemonic, however you remember it. So we'll have kilo, hecta, deca, then our base unit, deci, centi, and milli. So for meters, we'd have kilometers, hectometers, decameters. For deca, you use DA because we have two D's. We have a deci and a deca. Deca will be DA. Deci will be just a D by itself. We have decimeters, centimeters, and millimeters. Looking at grams, we can have a kilogram, a hectogram, a decagram, just a regular gram, decigram, centigram, milligram. So how you can use this device is look at the problem, look at the units for look at the unit that has a number on the device, put your pencil on that unit, and move over to your new unit, counting how many jumps it took, and noticing the direction of the jump. You will move the decimal and the original number the same number of spaces in the same direction. So looking at, for example, 56 centimeters, if you wanted to convert it into millimeters. So actually, I will use the PowerPoint and go back and do more examples. So we're going to start at centimeters, and we're wanting to go over to millimeters. That would be one hop to go from centimeters to the right millimeters. So you take the decimal and move it over once, introducing a new zero. So 56 centimeters is the same thing as 560 millimeters. So to convert 7.25 liters into kiloliters, we start at the base unit, L, and we count how many hops it takes to go over. So you go over to decaliters, one, and another one for hectometers, and then another one for kilometers, so 3 hops in total. I like to put a lot of zeros in front of the 7, and then start adding hops over. So 7.25 liters is equal to 0.00725 kiloliters. I hate this PowerPoint because it doesn't include the leading zero. Whenever you write a number, you should always, if it's less than 1, you should always include the 0 before the decimal. So it should be 0.00725. So we have this method, which I don't like. So we have King Henry died expectantly drinking chocolate milk. So suppose I wanted to convert 578 centimeters to hectometers. So I'm beginning at C and count how many hops it takes to get to H. 1, 2, 3, 4. And I'm moving toward the left. So begin by writing the number. I like padding zeros. I'm going to be moving 4 over to the left. 1, 2, 3, 4. So 0.0578 hectometers. 1, 2, 3, 4. 1, 2, 3, 4. Make sense? Now, I like using pure math and not doing any mnemonics. So we have kilo, we have hecta, we have deca, we have our base unit, and then we have deci, and centi or centi, and then milli. So our base unit is just 1, our 10 to the 0. This would be 10 to the 1, be 10 to the 2, this would be 10 to the 3, this would be 10 to the negative 1, 10 to the negative 2, 10 to the negative 3. So if I wanted to convert this, 578 centimeters, I can replace the C with the scientific notation of it. 578 times 10 to the negative 2 meters. And then I can realize that I can move over one. Let's see how best to explain that. So I need to move over 1, 2. So that'd be 5.78 times 10. And I'm adding going to the left, so that'd be 10 to the 0 meters. Fixing up scientific notation. And then if I wanted to convert to hecta, so once I get into my base unit, that's the equivalent of 5.78 meters, I can convert it. It's probably not the best example. What you could have done is take this, plug it into a calculator, and output this. Is probably the best example I've just said. Okay, just forget that. Use the mind. It's something that's difficult for me to explain. Yeah. So this is from Mrs. England stuff. I do this pure math. And I just realized how I do it is probably too complicated to explain to you to pick up. So how I look at this is equal to 578 centimeters, which is the same thing as 578 times 10 to the negative 2 meters. I then, if I want to convert into hectometers, what I would do is divide by 10 to the second power, and then plug that into the calculator. I plug that into the calculator. I get 0.0578 hectometers. So I rewrite it in this form, and then divide by whatever I needed to convert to. But doing this, you have to understand why I'm dividing, and I can't really explain it other than by instinct. That's why I'm saying, it's probably better to use a mnemonic than just use pure math without any explanation. Whatever is more comfortable for you to do. So 1,000 meters is what? Is equivalent to 1 millimeter, 1 kilometer, or 1 decameter. Kilometer. 0.001 grams would be equivalent to what? Milligrams. 0.1 liter would be what? So that would be moving the decimal place 1 over to the right, so that would be deci. and then 0.01 would be centimeters. So you need to move it over 2. So it gives you 0.01. In order to put the decimal behind this, you need to go 1, 2. So 1, 2 is centi. This is what we got. So measure numbers. When you use a measuring tool to determine a quantity such as your height and weight, these numbers you obtain are called measured numbers. They are estimates. They are not precise. You do not know your exact height. You can't measure anything exactly. You have to estimate some digit. There's going to be some level of uncertainty. In science, we have a precise way of doing this. A digit that must be estimated is called uncertain. A measurement always has some degree of uncertainty. And what you do is you record certain digits and the first uncertain digit, the estimated number. So I'll give an example. So graduated cylinders show each line representing 1 millimeter increments. The instrument is accurate to the ones place, therefore the estimated digit should be the tenths place. For scaled instruments, you have to estimate it. So liquid volume of this, or if you remember, you measure from the meniscus to the bottom of it, and you can see it's around 43. Note that you would write 43.0 because you don't know precisely if it's above that line, on that line, or under that line. You have to estimate it when looking at it. Let's do so let me show you reason why. So we have a very formal way. So let's say that something is exactly at 50 milliliters, or around 50 milliliters. If you were to record the answer 50 milliliters, what this is indicating is that you are unsure or uncertain of this digit. Well, that means you're saying this is somewhere between 40 milliliters to 60 milliliters. That's a huge difference in value. Technically, you are really uncertain about. If you're really uncertain about it, you could be anywhere between 0 milliliters and 100 milliliters, or 99 milliliters, or whatever. You are very uncertain about that. And that's a huge difference because you can't measure anything exactly. What you would say is you look around it, and you would look and put that it is 50.0 milliliters. That's telling you that you are uncertain about this place. It could be 49 all the way to 51, somewhere between these two numbers. Because we can't measure anything precisely, this is how we keep track of how precise a number is. Make sense? So all measurements have some degree of uncertainty. When measurements are recorded correctly, it must be written with a digit of uncertainty, an estimated digit, and a unit. The last digit in any measurement is the digit of uncertainty. It's the one that you do not know the precise value, and you can randomly change it, basically. So let's go over accuracy and precision. Accuracy compares a measurement to the true value. So it's talking about Um, is the measurement close to the correct value, or centered around the correct value? So, looking at these two examples, which person is more accurate? If the correct value should be 17. Who? So who would be more accurate? Who is closer or more centered around the correct value? The correct value should be 17. It'd be Susan. So, in science, we try to maximize both accuracy and precision. In common language, we don't use the correct, true meaning of accuracy and precision. A lot of times, a lot of people mean a combination of both. So let's look at precise. Precision describes how closely measurements are to each other and how carefully the measurement was being made. So which one of the three is more consistent, or more doesn't change that much? It'd be the first one. So the smallest value is 18.2, largest value is 18.4, so there's a difference of 0.2. Other one has almost a full 1 point difference between the smallest and largest. The last one's even worse. So looking at this one, Amy is now more precise in measuring the book. Her values don't change that much. So when we're making measurements, we're only as good as our tool is. Our tool could be off, and we also could have be using it incorrectly, and it could be varying a much. When we try to measure values, what we're looking for is one, to get an accurate data, meaning accurate value, meaning that we'll be close to the correct value, and also we try to be precise. We don't want to, if I ask you to measure out 100 milliliters, I don't want you to every single time you get 100 milliliters, go 60 to 120. But at the same time, I don't want you to constantly bring back 90 millimeters. So you need to be both precise and accurate. Where this gets people is, for example, in this scenario. So imagine you're throwing darts and you're trying to hit this dot. If I'm hitting all around it, I would say that's very accurate, even though you miss constantly. Now then, another example. Imagine someone is constantly missing and hitting at this corner. I would say they were very precise, even though they were far away from the target. They're very consistent. So, left image, what would you say it would be? What's its accuracy and precision? Yeah, we're trying to hit the very middle. So you have to have high accuracy and high precision. What about the right image? And low accuracy. So high precision, low accuracy. What about the left image? So low accuracy is random. Low precision is again very random. So it's low accuracy because it's far away. Some of them are very far away from the center. It's low precision because it's so random. What about the middle one? So low accuracy but high precision. And the last one would be considered high accuracy and high precision. Um, so a lot of times experiments require repeatability, so you need to be able to repeat the experiment. In order to repeat the experiment, you need to have high precision. But also, in order to get the actual values used in the thing, you need high accuracy. And there's also a trade-off. So some tools, for example, the more accurate you get, meaning the closer you are to a certain value, or the more accuracy you improve, or I should say, the more precise you get, it can start deviating from the correct value. Usually, other things is kind of complicated to give an example. I know one example would be if you're trying to measure something using electricity, you can get a roundabout, but whenever you pump in like a high amount of electricity, static electricity will start coming off, and it'll cause your value to deviate because you're trying to be more precise than your machine is actually able to do. So that's it for today. Any questions? It's a short lesson.